Okay. Hi everyone. So today we have Kate Huntington with us. Very excited to hear about her mega everything, it sounds like. A little bit about Kate. So she did her PhD at MIT and then went on to do a postdoc at Caltech. And now she is a professor at Washington. So yeah, a little housekeeping. So we'll keep the chat off. Kate will do her talk and then we'll kind of switch it on towards the end. And you can add your questions in the chat. And we also have the option to unmute yourselves and ask directly. And next week, we will have a break, but we'll be back the week after with a talk from Dirk Schuller. Okay, so Kate, the floor is yours. Go ahead and share your screen.
Okay, let me get our faces off of here. All right, so thank you all for being here. As I mentioned to the organizers, this is actually the first full-length talk that I've given since the pandemic. It's been an exciting time of the pandemic. So I'd only done, sort of the short 12-minute style talks since then. But I'm excited to be here and have this sort of longer format. And yeah. So hi, everybody, and thanks for inviting me. I'm Kate Huntington from the University of Washington in Seattle, United States, which is on the ancestral lands of the Coast Salish peoples, including the Duwamish, Puyallup, Suquamish, Tulalip, and Muckleshoot nations. So I'm interested in the evolution of Earth's surface and how it reflects the interactions of tectonics, surface processes, and climate. Most of my work uses geochemical methods to tackle these large-scale sort of paleotopography and climate parts of the problem. But today I'm going to spare you all the geeky sort of clump isotope geochemistry stuff and focus on an extreme example of the coevolution of surface processes and tectonics, the Tsangpo Gorge region of the Eastern Himalaya-Tibet, pictured here. And what I hope to show you is that to understand its history, its processes, and their impact on the largest source to sink sedimentary system on Earth, we're going to need to look at a wide range of scales in space and time. And so we're going to look at everything from single event flood deposits and hydraulics to erosion and deposition over thousands of kilometers and millions of years. And so I'd like to thank my funding sources, especially the U.S. National Science Foundation, Tectonics and GLD programs, and the Quaternary Research Center at the University of Washington. Let's see if I can advance. I also want to acknowledge co-authors and collaborators and just colleagues, both at UW and elsewhere, who have contributed to this work and to my thoughts on it, and also supported our analytical efforts. But especially I want to highlight my students and former students, many of them now turned collaborators, whose research forms the basis of what I'll be presenting today. Especially I want to highlight Carl Lang, now a professor at Georgia Tech, Mike Trzaskowski, Susanna Mori, my current student, and Mahathi Manjapudi, who was a high school student working with us, who's now at Stanford. And I'll be highlighting their recent papers. And finally, I just want to acknowledge the many members of the earth sciences community, many of you who I just noticed were in the audience today, whose publications and collaborations have contributed to my thinking on this topic, in particular as I worked on these two recent reports, the 2018 Tectonics Community Vision Report, vision document on the left there, and also the 2020 US National Academy's Vision for the Earth Sciences Earth and Time report on the right. And so the PDFs of these are free to download at the links I'll paste into the chat, or I guess I can't do the chat, but the links shown here. And so, yeah, working on these with so many of you has really shaped my thinking. And as both of these reports and many other studies over the past couple decades have highlighted, one of the most exciting developments in the earth sciences over the past couple decades, I think, has been this idea that atmospheric, surface, and deep earth processes may be coupled in complex feedbacks. And this has really broad implications for how we understand the interconnected earth system. And so, for example, it's been argued that coupling in convergent margins could work like this. You'd have deformation that builds high topography, which then leads to orographic effects that focus precipitation. Then precipitation is channeled in rivers and glaciers, resulting in focused areas with high potential for erosion. That intense erosion can then remove material, steepen that local geotherm, which in turn weakens the crust, changes its rheology. That could, the idea is that it would then promote further deformation concentrated in a region in a positive feedback that could occur. And so this idea, we're going to look at it at the Himalayan syntaxes. So the Himalayan syntaxes, these are the great orogenic bends around the corner of the Indian plate indenture, shown here with my arrow. And it's been argued that together with the St. Elias syntaxis in Alaska, may arguably represent the best evidence of a natural landscape in which you could have this kind of a localized positive feedback between erosion and deformation anywhere on Earth. And so this area we're going to focus on today is of the Eastern Himalaya, where you have the Yarlung-Siang-Brahmaputra River system that makes this hairpin turn through the high Himalaya. And as it does, it carves through these two higher than 7-kilometer peaks of Namche and Galapari. And as it does, it carves this really steep 2-kilometer nick zone of the Tsangpo Gorge. And in this area, precisely where you've got the big mountains that are sliced by this big river, is this area of active deformation and rapid rock uplift with really rapid modern erosion rates and highly localized rapid exhumation for at least the last few million years. And this area of localized exhumation and erosion really dominates the sediment load downstream. In fact, sediment from this small area of the gorge shown in red, which is just about 2% of the Brahmaputra drainage, which I've highlighted in yellow, sort of schematically, it dominates the modern Siang River bedload at that yellow star. So even though it's a tiny aerial proportion of this region, it really dominates that signal. And we also know that sediment from this region may also have an outsized signal in the sedimentary deposits all the way into the deep sea Bengal Fan, thousands of kilometers downstream and offshore, as I'm highlighting down here at the bottom. Move that. And so, people have even argued that erosion and transport of material from the gorge all the way to the deep sea Bengal Fan may have been aided by glacial outburst megafloods. Indeed, this area is abundant evidence for glacial and landslide dam lakes that failed and produced catastrophic outburst floods throughout the Quaternary and today, all throughout the headwaters of this area highlighted in yellow on the map. And so here we go. We've got this localized region with high Himalayan mountains, a steep gorge, high relief, powerful Yarlung River, megafloods, and rapid exhumation. And all of these things coincide spatially. It's just such a dramatic landscape with this extraordinary relief shown in this photo. And it raises a lot of questions about the history and processes of the region at a wide range of scales. And in particular, we're going to look at the questions of, how long lived is this feature, is this situation? What could have triggered this apparent coupling of rapid rock uplift and erosion, or at least their spatial coincidence in this place? What's the role of infrequent big floods versus the powerful annual monsoon river flows in maintaining rapid erosion over millions of years? And what are the implications of all of this for depositional records in the largest source to sink sedimentary system on Earth? And so we're going to address these questions about the timing, the trigger, erosion, and deposition in two main parts. First, we're going to look at the relative timing of the river course being established through the gorge and the onset of rapid exhumation to study what might have initiated their coupling of rapid erosion and rock uplift. And so the punchline is going to be that the timing that we get from detrital provenance and thermochronology data rules out river capture as a trigger, and instead suggests that it's really a tectonic driver for rapid exhumation, and it's just erosion by an antecedent pre-existing river that is keeping place. Next, in part two, we're going to look at the mechanisms by which erosion keeps up with rapid rock uplift, looking at different magnitude flows. And so we're going to use flood deposit provenance and hydraulic modeling of floods and show that not only is there great potential for megafloods to preferentially erode the gorge, so not just erode more, but actually focus erosion in different places spatially, but megafloods also have profound effects of their deposits on river processes. And ultimately, I think this will inform our understanding of the erosional and depositional legacy of these megafloods all the way from the source to the sink. Okay, so first we're going to start with when was the modern river connection through the gorge established? To look at this, we can just look at the distorted modern drainage pattern in the region that really just suggests a complicated history. And potentially with antecedent rivers like this one being potentially being dragged as passive markers of crustal deformation has been proposed. And also ample evidence for drainage reversals and capture over the last several million years. And so this has led to a lot of models for the establishment of the river connection through the gorge region, highlighted in this box through here. And this would have implications for when the coupling of river erosion and tectonics could have been established. So zooming into that box, we can look at some end member hypotheses. First of all, some have suggested that capture of the Yarlung, perhaps around 3 or 4 million years ago, by headward erosion of a Himalayan tributary. So here's the Yarlung. And this is what headwater capture could have looked like. This may have rapidly increased drainage area in this zone over here, and stream power through the steep reach, and perhaps triggered a feedback with deformation and exhumation. And so in this scenario, the Yarlung here would have originally drained eastward through the Parlung and out to the south, somewhere else, perhaps the Irrawaddy in the Eocene, or maybe the Lohit. But at any rate, river capture would have occurred sort of in this zone. And then later on, it would have had the Parlung reverse its course and flow out through the Siang here where it does today. So the Yarlung-Siang-Brahmaputra. Alternatively, it's been proposed that the river was antecedent and got dragged along the suture zone until it eventually captured the Parlung. So getting dragged along this way and eventually capturing the Parlung and again reversing its course. In this scenario, it would have been passively steepened in response to uplift of the Namche Barwa Massif later on. And so to test this idea of river antecedents and look at the drainage evolution, we can exploit the fact that bedrock zircon uranium lead ages are diagnostic of the source area region. So specifically for this part of the talk, we're going to be looking for when detrital zircons with crystallization ages younger than 250 to 300 million years that are from the Ganges batholith belt shown here schematically in this green oval, when they appear in the foreland basin. So rocks eroded from here when they connect through and appear in the foreland. And to see when the connection of the Yarlung through the gorge region and out through the Himalaya to the Brahmaputra was established. And we're going to look at these records in various foreland basin sections of the Sawalika units shown with the yellow stars here, going back to the Miocene. And this I want to highlight is, I'm highlighting the PhD work of Carl Lang. But first, prior to that, work by Sina and others in the Kieman section, highlighted there with the green star on the left, found these younger Ganges zircons at least through the Subansiri formation down to about 11 or so million years ago in this section over here near Khmer. But they argued that this was actually showed up there due to temporary connection of the Yarlung through the Subansiri and not connection through the gorge region into the Siang. And so to test this hypothesis that it was a Siang connection, we went upstream to the Sawalika foreland basin deposits exposed in Lokavali section along the Siji River in Arunachal Pradesh, India, mostly on the lands of the indigenous Adi peoples who generously facilitated our work. So at Lokavali, so here we are in the middle black or green dot here, we find these Ganges zircons with uranium lead ages showing provenance from west of Namche Barwa. So these Tibetan zircons could, in theory, I guess, have been delivered from the east through the Lohit, or from the east from the Lohit, except for we don't actually see ages from the Bomichayu plutonic complex, which would have been there up here if it would really dominate the signal if the Paleo River was was getting its Tibetan zircons from this path. Another smoking gun piece of evidence that we're talking about a connection really through the gorge for the Siang is that this section is super proximal to the Siang, but more importantly, it contains diagnostic Siang aborvolcanic rocks that crop out basically around here and nowhere else. And so this idea is also corroborated of this connection being established by to the base of this section by 11 million years ago or so, is corroborated later by detrital studies by Yanni Neiman's group, including even more proximal deposits studied by Govind et al., showing that this connection may have been established as early as 13.5 million years and potentially earlier. And so with all of that, I think we can safely say that the river connected through the gorge since at least 11 to 13.5 million years ago from detrital provenance, and likely earlier. And so then we want to know, when did rapid exhumation begin? So for this, we're going to look at cooling ages, which record the time since a mineral cooled below a certain temperature. And temperature increases with depth in the crust, as you can see with my little schematic warm colored dashed lines here. So as rocks are exhumed or brought to the surface via erosion that's happening up here, the rocks cool along the trajectory of this black arrow. And at a certain temperature for each mineral system, the clock starts ticking, and the faster the exhumation, the less time the mineral sort of stopwatch has to tick before it gets to the surface, and so the younger cooling ages. That material gets eroded so that modern river sediment cooling ages and the sediments in the foreland basin are about the same or similar to the local bedrock at any given time, which in the gorge area means they're super young. And we can look at the signal of what cooling ages were at the surface back through time in basin deposits using the idea of lag time, which is the difference between the measured cooling age and the depositional age. And so again, short lag time means that you have rapid exhumation and cooling in the gorge area at the time of deposition. And so modern lag times from zircon fission track cooling ages, they're extremely short, about half to about 1 million years, consistent with the young cooling ages in the gorge and rapid erosion today. So we want to go back through the foreland basin and see when those short lag times, when these young cooling ages first appeared at the surface. And so to do this, we're going to look at a plot here of depositional age going back in time versus lag times, that difference between the cooling age and the depositional age. You see at the surface, those data I showed from Enkelman and others for the zircon fission track, and then the slightly higher temperature sensitivity of white micas, their youngest age components that we measure in the Siang River here at about 5 million years. And so if we go back through the section, and in particular, we're looking at parts of the, double dating these zircons, so we know that they're actually from the gorge region because we've got their uranium lead ages as well. We can see that the lag times really stay ultra short for at least the last 5 million years. But then they increase, and so they're getting longer, indicating that sometime before those appeared at the surface, you were eroding more slowly. And so we did some simulations with a thermal model, P-cube, and estimate that the timing, the onset of rapid exhumation, and we're talking like a 5 to 9-fold increase in exhumation rates, occurred maybe around 5 to 7 million years ago, perhaps slightly earlier. And so this is going from essentially rapid Himalayan rates of 1 to 2 kilometers per million years up to the extreme rapid rates of the gorge region today of 5 to 10 kilometers per million years. And so this is consistent with modeling of regional bedrock data sets by Zeitler and others, and estimates from the detritus in Bangladesh. And so with all of this, this suggested that, you know, this rapid exhumation initiated in the late Miocene and was ongoing by the Pliocene. And so our timing of events from detrital provenance and exhumation record, if we're going to summarize this, we've got the onset of rapid exhumation at 7 to 5 million years. But we find it does not coincide with the drainage change, which occurred at least or earlier than 11 or earlier than 13.5 million years ago, likely before that. It also doesn't seem to coordinate with the timing of Quaternary climate change. And so really, this doesn't look like an obvious fluvial or glacial erosion driver for this sort of situation being set up with the rapid exhumation. Rather, we suggest it's a tectonic driver. where the localization of deformation and exhumation at the syntaxes may have been initiated just by the indenter and subduction geometry as proposed by Bendick and Ehlers. This idea is also in line with the discovery of incised and sediment-filled section of the Yarlung River, which suggests that more recent incision and steepening of the gorge were a result of rapid rock uplift, not its cause. Okay, so we've got this situation, and now we want to know what processes maintain rapid erosion in the gorge. I told you about this older work because I think it's important context, but now we're just going to focus on erosion processes. And so you geomorphologists who have been waiting for this part, here we go. So we know that patterns of stream power for the modern river suggest really high annual erosion rates for the gorge. And so we can see this red zone over to the right here, oops, that's showing you there, is extremely high stream powers on the map. You can also see peaks in stream power on this plot of elevation versus distance, the longitudinal profile of the river with the Tsangpo Gorge highlighted in red. You can see these peaks in stream power shown here that coincide with that area. And also you can see that these bedrock incision rates set the pace of hillslope erosion in this area because it's got threshold hill slopes. So this also coincides with high measured landslide erosion rates shown in the dark gray measured by Larson and Montgomery. So this is sort of the annual river processes, and we know that they are really big in this area. But also, we know that the river was dammed repeatedly, as you can see in this headwater area where the moraine dam is indicated. In fact, we have evidence of many reconstructed paleo lakes. A handful of these are being shown in this picture with these turquoise and magenta colors, and many possible impoundments. So basically all these little black dots all over the place. So these are valley blockages and glacial and landslide dams. And these include Quaternary glacial lake outburst floods, some reconstructed as big as 800 cubic kilometers of impounded lakes that catastrophically drained as megafloods, such as proposed here in this photo by Bernard Halle, this is Namchibarwa, of moraine dams that would have impounded enormous lakes at a couple of levels here. Also, we know that landslide lake outburst floods are important today, and in particular, the second largest outburst flood on record, the Yigong flood that happened in May 2000, happened right here in this little area, and again, went through the gorge. And so we've got the river monsoon flow, these historical landslide lake outburst floods, and the prehistoric glacial lake outburst floods that vary greatly in magnitude. If we think about their discharge sort of in terms of Olympic-sized swimming pools worth of water per second, we're talking on the order of 16 swimming pools per second rushing over your head during the monsoon, 40 in terms of that historical landslide dam outburst flood in the Yigong, and that happened in 2000, and another from the same place that happened 100 years earlier in 1900. And then these prehistoric glacial outburst megafloods are just another order of magnitude, 400 Olympic-sized swimming pools per second rushing over your head. So that begs the question, how does erosion of this area scale with discharge? And that's a hard one to answer. Maybe what we can answer more specifically with the evidence we see in this area from the geologic record, we can ask, how do different magnitude floods have, do they have different erosion patterns? And this would be interesting because we've looked at this area with its great spatial gradients in exhumation rate. We want to know what are the processes by which the river is keeping up. So we can study this by looking at the sand deposits from single flood events, as well as the modern river. Individual flood events are recorded by slackwater sand deposits all throughout the Siang River Valley. And this includes deposits from the 2000 Yigong flood, that historical second largest outburst flood on record, as well as the previous flood that occurred 100 years earlier. And these are slackwater sand deposits that are draped all across the topography in these fine, often laminated deposits of fine to medium sands. We also find analogous deposits that are really sedimentologically very similar, again, draped over topography, that record prehistoric megafloods at different levels within the drainage. So these are flood slackwater deposits, again, that we have these sands, but they've got soil development on top, and they're typically capped by landslide deposits and more soils. Often we see these stacked and separated by landslide deposits as well. And so with all of these resources at our disposal, we want to think about what these deposits can do for us. But first, I want to show you my favorite, pretty much my favorite outcrop ever in all of geology. So it's very pretty. We've got these folded bedrock here at the bottom, landslide deposits, this draped megaflood deposit, and more landslides and soil development on top. And so this is sort of the interpretation. We've got the folded abrovolcanics at the bottom. But why I love this is not just because it's photogenic, but because the scale of it. This is Mike Trzewski, and he is something like, I don't know, 1.8 meters tall, probably. So this is just colossal. And these deposits can be up to hundreds of meters above the modern river channel. And these are so what the modern river channel looks like. And it's these, extraordinarily steep slopes and at the threshold for landsliding. And so you wonder, how could you have depositional records in this really erosive landscape? And first off, these flood sands tend to be deposited in hydraulically sheltered areas, but they tend to be rapidly covered up by landslide deposits, which can armor them and save them from future erosion, preserving them for our use. So we've got deposits from the modern river. We've got these bigger events from the historical floods and the biggest glacial outburst flood deposits. And again, now we want to ask if we can use them to figure out if there are different patterns of erosion for different magnitude flows. So again, we'll go back to our zircon uranium lead ages that are diagnostic of our source area, with the Tibetan sources highlighted in green up here north of the Indus-Yarlung-Suture zone, with the Himalayan sources that have different age populations of around 500 million years highlighted in orange, and this includes the Gorge region. And specifically, this bullseye right around the Gorge and Namche-Barwa Massif, that's the only place with these young, less than 30 million year old anatectic zircons. And so this is an idea that Stewart et al. Way back in 2008, first had the idea to look at the modern Xiang River sediments to see where the material was coming from and where the river was eroding today. And they found that 45% of the zircons in the modern Xiang River sediments are from the Gorge area, which is just 2% of the total drainage. And so this they interpreted to indicate that the river focuses erosion in the Gorge today. Carl Lang's 2013 paper found a similar proportion of gorge-sourced zircons in deposits of the 2000 Yagang flood. But in their analysis of megaflood deposits, they actually found double those gorge-sourced zircons. And so the interpretation or the question that's raised is, does this mean that megafloods focused erosion even more in the gorge? And so in that sense, causing different patterns of erosion in flows above a certain magnitude. And so since then, we've reframed how we think about this question to think about what the zircon provenance really means in terms of erosion patterns and where the sediment in a single event flood deposit comes from in a more nuanced way. So to make a very long story short, a lot of data and a ton of work by Mike Trzewski, including compilation of thousands of more zircons from the source area, landslide lake outburst flood deposits, modern Xiang River deposits, and 1,600 new zircons from 11 new megaflood deposits, as well as single grain luminescence data and radiocarbon dating of these sorts of deposits. All of this, we've basically started thinking about it in terms of megaflood sands coming from impounded lakes, erosion immediately downstream of the impoundment, and sediment reworked along the way. So it's not simply sort of originally how we're thinking about it, megafloods triggering landslides and the fine material from the landslides ending up in the deposits, but really all of these sources combined. But our large data compilation has a couple of take-home messages. The first is really interesting in that it suggests most of the deposits were from megafloods that were sourced from impoundments in the Yarlung drainage at or to west of Namche Barwa, rather than possible impoundments over to the east. But the second, and what's most important for our discussion here, is that compared to the active bedload in the Siang River and historical outburst floods within the same drainage area, this large data set shows that megaflood samples still contain disproportionately large amount of zircons eroded from the Tsangpo Gorge. This overabundance cannot be explained by sediment reworking or other effects. So basically, although we've done all this work to try to disprove the idea that megafloods focus erosion in the gorge, we can't. And so really all the data we have so far from megaflood deposits shows this preferential erosion of the gorge area during high discharge events. In other words, we're suggesting that megafloods don't just erode more than smaller outburst floods or the annual monsoon, but they erode relatively more in the gorge region. And so stay tuned for radiocarbon and single grain IRSL constraints on the deposit age and provenance as we continue to try to disprove this working hypothesis that we're stuck with for now. So for the final piece of our discussion today, we're going to get away from these provenance studies and zircons and ask the same sort of questions about the erosive potential and erosion patterns that we see using hydraulic simulations of outburst floods. And to do this, we're going to use GeoClaw software for simulating geophysical flows, and it's essentially implements the 2D shallow water equations over 3D topography. What this looks like is we set up a dam location on topography like I'm showing here. We fill up a lake behind it, like shown in the image on the right, and then instantaneously fail the dam and see where the water goes. We measure flow depth, direction, and speed, and all the goodies you can derive from those values. And we're going to do this to learn about the relationship between the high relief topography of the Himalaya and flood hydraulics. So there have been megaflood, outburst flood modeling studies before, but this one is really about going through that area of intense high topography and high relief topography. We're going to try to learn more about the relationship between it and understand the erosional and depositional fingerprint of these massive floods. So we're going to start by simulating the second largest historical outburst flood on record, which occurred in, again, this one that occurred in the year 2000 on the Yagang due to a failure of this landslide dam that impounded a lake that then failed. And this went through the gorge. And so on this map, you can see here's the Yarlung-Siang-Brahmaputra River system that we've been talking about, with the start of one of those reconstructed lakes, just for reference over here, that goes way off your screen. And here's the gorge region, and here is the impounded Yagang Lake. And what we're going to do is simulate the outburst flood from the Yagang, and it's going to go through the gorge and all the way through the high Himalaya and along this pathway for 460 kilometers, all the way out to where it exits the range front in this dashed line. And so Mike Drzeski simulated these floods and also did a ton of field work and remote sensing measurements to try to ground truth the flood to say, are we really capturing this? Are we able to model floods through rugged topography like this? And so some of the evidence we used to test our modeling skill was observations of the high water marks from the year 2000 flood that we measured in the field. So for example, you can see the monsoon high water mark where you've got the bare bedrock showing, and this is this change in vegetation we observed and first started observing in 2008 between what was just the rapid vegetation replacement after having it been stripped away from the 2000 flood. So we compared two measurements at a bunch of different locations. For example, these areas shown in the yellow boxes. We also compared the results to observations of the dam breach, the flood timing, and inundation and discharge estimates that were made in a variety of areas immediately downstream of the breach up here, as well as at the range front in the town of Pasigat. And all of this gave us high confidence, as well as remote sensing measurements where we essentially compared remote sensing measurements with things we had seen in the field down here, and then made those observations in the Tibetan part of the study area where we couldn't access things. So all of these observations suggest we do a good job of matching inundation and many of the major features of the flood. And so now we're going to look at some flood simulations. This is a simulation of the first 90 minutes of the flood. And so you see the impounded lake, and you see the topography refining as we go along. This is adaptive mesh refinement. That's basically a computational efficiency thing that only makes calculations where the water is. We track flow depth here, you see, and you can see that the flow is getting really deep as the flood progresses. Just above, basically just off your screen, there's a constriction where the gorge occurs, and this is backing up water. You can also see the big inundation up the tributary here of more than 5 kilometers. Next, I'm going to show you the same kind of simulation, but this time plotting shear stress. And so for the shear stresses, you can see these extremely high values immediately downstream of the breach, like other studies that predicted. But you also see hotspots of really high shear stresses, again, associated with these large scale topographic features like constrictions or ridges that protrude into the river. And this is really telling us that the valley morphology above the channel, for example, these constrictions, controls the hydraulics and shear stress patterns, including the location of hydraulic jumps. And so a big take-home message here is that the valley morphology is setting up flood hydraulics in ways that would cause us to expect it to focus erosion and sediment transport in different areas than we would predict for annual flows. And so this is getting us at the idea of maybe these bigger events are actually eroding in different places, preferentially than the annual flows. But another consequence of these shear stress patterns is deposition. Large depositional boulder bars in the Siang Valley, many of which have boulders that are too large to be transported by the annual monsoon flows, such as this one to the left. Now look at the scale of this thing. This boulder bar is 1.5 kilometers in length. It occurs at the inside of a meander bend, which is not unexpected. This is on the Po River. And so you could expect deposition of boulders on a point bar like this. However, the critical shear stresses needed for incipient motion of the large boulders on the surface, which are 5 meter median intermediate axis, is something like almost 5 kilopascals. And we know that both from imagery before and after the flood and our simulations shown here on the right, where here I'm plotting the bed shear stress, that this outburst flood would have inundated this bar. And it turns out that our shear stresses that we measure on this area are enough to cause motion of these bars up here upstream, but then this gradient happens where you drop the bed shear stresses precisely where you're starting to deposit these boulders here. So this is all suggesting you're setting up a situation where you can transport large boulders and you would expect to drop them right in this spot. And so the large particle sizes here and just the scale of the feature are not something that the regular river can do. And this, combined with our modeling, is really consistent with a direct link to outburst floods. And so it turns out we've mapped about 75 of large boulder bars in the Siang River Valley downstream of these flood areas. And all of these 75 that we've mapped are in locations that are not expected for that you would not expect to find boulder deposition just by the modern river. Things like cut banks at the outside of a meander bend, as opposed to, say, a point bar location like in the last example. So in these, our simulations show shear stress magnitudes and spatial and temporal gradients consistent with deposition of many of these bars. And so this could be, for example, I'm showing bed shear stresses here, a place where you would expect deposition during a flood in this area, again, due to this drop in bed shear stresses, high shear stresses that could move the boulders and then dropping those boulders out of transport here. But so this explains a lot of the boulder bars, but some of them along the flood pathway cannot be explained and actually need bigger floods than this landslide lake outburst flood to move. And so this is really important if we think about boulder deposition, because boulders are going to armor the bed, they're going to extract momentum from the flow and affect subsequent erosion patterns and potentially processes of lateral erosion. Boulders moved and deposited by these outburst floods could be abraded but not moved by meteoric floods, and so they could become long-lived features of the landscape. And so I think this highlights the idea that outburst floods change both the magnitude and spatial pattern of erosion potentially, as well as depositing boulders that impact subsequent erosion. And so this was, sort of thinking about the comparison of the modern monsoon floods versus that modern outburst flood. And now we want to think about how this scales up to a megaflood. And so to do this, Susanna Mori has been simulating a reconstructed megaflood sourced from a lake impounded by a glacial moraine here, the lower of the two at Namche. And this was the reconstructed lake mapped by Montgomery et al. In 2004. And this is the resulting flood that followed the pathway. So here's the impoundment, here's the lake, it would have filled up, and here's the pathway through the gorge region and out through the Siang River. And so now we're going to zoom into this little area circled in red here for the next slide that I'm going to show you for some of the results. And so we're going to zoom into results for this area because it has really interesting changing valley morphology. And we also have a lot of field observations for this area. So you can see here in this cross section A, the valley is narrow, and in B, you've got a big terrace and the valley is wide. So before I start Susanna's videos, I'm going to point out a few things. The first video you'll see is of flood power up here, while stream power, which we interpret to indicate erosional potential of a river, boils down to the relationship between annual discharge, channel slope, and channel width. We calculate the analogous quantity of flood power as a product of shear stress and depth average flow velocity at a given point following Denlinger and O'Connell. Anything in red over here, closer to 10 kilowatts per square meter, has a higher erosional potential, and anything in blue, closer to 5 kilowatts per square meter, has a higher depositional potential. We're also interested in what size sediment this flood can move, so we'll look at shear stress. Susanna cleverly scaled the color bar to shear stress required to initiate motion on a block of a given diameter. Here we've got big blocks up to 8 meters, and here we've got smaller than sand sizes at the other end of the spectrum. And so now we're going to look at how the hydraulic patterns vary in space and time and how they depend on inundated topography at every time frame, and this is an hour. So on the left here, we're going to be looking at flood power. And first thing you'll notice is that just the great extent of inundation that you have around this terrace area and the significant backflow you see up these tributaries. Also, you see that you've got high flood power up here in this narrow region, and it drops off below. So you can imagine transporting boulders here and dropping and depositing them there. And in shear stress, you can see a similar thing, similar to flood power. We see high shear stresses in this upstream reach, more than we do in the terrace, again, likely to cause depositional changes. So here we could be eroding, and here we're more depositing. And importantly, you can see how the valley morphology, whether it's narrow or wide, is going to directly influence the hydraulics and therefore the erosional and depositional patterns during megaflood. And what's especially cool about this is that, okay, we knew this from the smaller outburst flood simulations, but Susanna's megaflood situations really highlight how different topographic features become relevant at different parts of a megaflood flow as flow depth changes and inundates different features, for example, like ridges. So you'll have to wait for her paper, which was recently submitted to JDR Earth Surface to learn more about that. Another important finding is that these simulated hydraulics are telling us about the potential to move big boulders all the way throughout, basically all throughout the flood pathway. And in particular, boulders that we're transporting here in blue up to 8 meters. We've got a lot of boulder bars in these areas. They're lithologies that are not local, so they must have been derived from bedrock channel or hill slopes upstream. And these megaflood hydraulics can move them. And so then the question is, like, what is an 8-meter boulder looking like? What size is this? It's like the size of a bus. So this is a lot of boulders, and we observe a lot of boulder bars throughout the flood pathway, many with boulders up to 5 meters or higher in diameter. And so here are some just in the Tuting area that I've circled, and we're going to look at this one to take a closer look. We're looking at the river. Our view will be in that direction. And this is what the Boulder Bar at one of the Boulder Bars at Tuting looks like, that were inundated but not moved in the historical flood. And if we take a closer look at these two locations on the left and on the right, for scale, we have people in these pictures, and you can see that just how large these boulders are. And they're covering bedrock, which really highlights how they can be armoring the bed. And so we can think about this legacy of outsized boulders being deposited in the channel during a megaflood, and what they might have in terms of legacy for channels and hill slope evolution, in terms of things like slowing upstream migration of nick points, maybe causing rivers with boulders causing steeper and more stepped profiles than rivers without them, or on the hill slopes, boulders preventing downslope migration of sediment. And so this is something that Susanna and our team is beginning to explore. And finally, I just want to highlight this idea that here now we're in the lower, more distal part of the flood pathway, this tributary called the Siam River. And so I'm going to show you what the flood looks like here. And again, we're doing flood power. And so you're going to see the regular Siam River flood that we saw before, but now you're seeing inundation up this tributary. And what you see on the right here with the shear stresses as well is that as the Siam tributary is inundated 60 kilometers away upstream of the confluence, both your flood power and the shear stresses are moderately high and then taper off. And so for most of the duration, they are capable of moving sand and gravel sized sediment in this area. This is a colossal potential for deposition in this area. It's an exciting result that matches what Susanna and Carl Lang saw in their last field season right before the pandemic, where they went to the Siam River and sampled a bunch of deposits that they observed and that they hypothesized has to do with deposition during megafloods. For example, this large sand deposit that's capped with the clay up above. So we're looking to test these hypotheses with, again, the provenance methods that we looked at before with the zircons. And thinking about the legacy of massive sand and gravel deposition during the megaflood, as well as the boulder legacy of the boulder deposition. And so in the end, it's not just megaflood erosion, but deposition during megafloods that is going to be critical to understanding the role of these big and frequent events in the evolution of this fascinating region. And so we've come a long way. We've talked about the relative timing of river course establishment and the onset of rapid exhumation, and suggest that it's not river capture, but a tectonic driver for exhumation with the river keeping pace. Then we looked at megaflood deposits and how they suggest preferential erosion of the gorge area during high discharge events. And we've looked at the erosional and depositional legacy of the megafloods. And so for 1 minute, I just want to highlight a couple of implications from source to sink. So to orient you, we've zoomed out. This has been our study region so far around the red star. And we want to ask the idea, could differences in glacial outburst megaflood erosion, where we preferentially erode and deliver material from the gorge area, could it matter thousands of kilometers away for these deep sea fan deposits? So here's the situation today, as described by Bloom et al. High sea level and a submerged continental shelf, so that there's limited sediment transport from the Brahmaputra out through the slope canyons to the fan. But during glacial low stands, you would have had sea level be lower, you're exposing the shelf, and the rivers make it farther out so that sand could potentially be transported through the slope canyons to deep sea more easily. So this is a really interesting idea because Jen Pickering and others have documented gravels and boulders in the transfer zone to the Bengal and in the Bengal Delta, and they require megaflood scale discharge to produce. And Lee et al. Reported wood in the Bengal Fan way down here, thousands of kilometers away, that comes from the high Himalaya, which they argue was transported by megafloods. So megafloods preferentially erode the gorge and glacial times, and megaflood transported sediments are preferentially preserved in the Bengal Fan because they're associated with glacial times. This could make for an even bigger impact of the syntaxis and its highly localized extreme erosion and exhumation in the sedimentary record, not just up here, but all the way to the sink. Okay, so we've talked about the interactions of fluvial erosion, climate and exhumation through the late Cenozoic, tectonic evolution of syntaxis, and today. And again, rapid exhumation, beginning probably 7 to 5 million years ago, was not caused by drainage or climate change. This suggested tectonic driver for extreme localized deformation and erosion and exhumation in this region. And then we explored processes, these megafloods, by which fluvial erosion keeps pace. And we find that high magnitude floods preferentially do erode the gorge region from those provenance data, with long-lived erosional and depositional legacy downstream. And so with that, I just want to again highlight the current and former students, especially who worked on this, other collaborators and colleagues, and thank you, and open it up for questions.
Thank you, Kate. Sorry, I had a moment there. Awesome. Thank you so much. That was super interesting. I have so many questions rolling around in my brain. So we don't have any in the chat right now. Wait for people to answer them. But I myself was wondering about lithology. I don't know if you mentioned at the start what the lithology is in this region. And I remember you saying in the gorge, you had these high zircon ages. Is that have an indication for lithology and erodibility there?
That's a great question. And so in the area where we've been able to access and conduct our fieldwork, which is south of the China-India border, that area has a lot of metasedimentary rocks. They're still quite competent and able to sustain really steep slopes. And then in the gorge region, we do have really sort of these anatectic rocks and really rapidly exhumed competent rocks. I mean, there have been ideas that, you know, the area has a lot of deformation, so fracture. Maybe it's not the lithology itself, but fracture patterns that might be most important. But overall, these are really pretty strong rocks. So it's not like we have soft, mushy sediments that are getting, boulders coming from upstream that are really competent igneous rocks or something that can smash them about. I think the rocks are pretty competent throughout, although there is a change in lithology. Although the lithologic change is really interesting for us because it tells us that the boulders weren't just, like, for example, in the field area that I highlighted, sort of in the middle of the drainage, those big boulder bars we were looking at, we know that they aren't just local landslide material that was reworked in place. We know that because the lithology does not match what the bedrock they're sitting on. And so we know that they had to have been transported from somewhere upstream, perhaps not that far, but at least tens of kilometers, and perhaps in multiple events being transported to that place.
Okay. So no questions yet, so I'll go ahead and ask another one while I'm here. So yeah, those boulders fascinate me, and the fact that they're just sitting there and clearly covering the bedrock as well. You showed a picture there. What kind of flood magnitude do you think can now move those boulders again?
Yeah, that's a really good question. And so so we know that they can be moved in the smaller of the reconstructed, so we did the Outburst flood. There were 2 reconstructed impoundments and likely others, but 2 established ones from Paleo Lake levels that Montgomery and all reconstructed. So Susanna modeled the smaller one. The bigger one is probably 10 times bigger. So we know the smaller of the 2, the megaflood we looked at, can move those boulders. At least our simulated shear stresses should have no trouble moving them. We know that the 2000 flood was not strong enough to move those boulders, at least in our simulations and the observations from local people who said that they didn't move. Probably big floods, but we know that nature will provide, or did provide during end glacial times, plenty big enough to move them. And so then the question is, how much could they abrade sitting there? How much could the regular river abrade them to get them to maybe smaller and then move them? And probably the answer is it would take a really long time. They don't even get inundated, many of them, by the modern monsoon. And even if they did, those are big big boulders and they would take a long time to abrade. But this is something that Susanna is trying to quantify, working with Charlie Shobe and doing some modeling of what the effects would be, and also see their effects on lateral erosion and the longitudinal profile.
Perfect. Okay, so we have lots of questions going in now. I don't know, Philippe, if you want to ask the first one.
Yeah, I can go. So we have a question by Ben Everett. So you suggest huge flood powers and shear stresses. For the bedrock channel, are you approaching levels at which cavitation will become an important erosion mechanism?
Oh, that's a really interesting question. So I haven't thought about cavitation. I guess I'm seduced by the ridiculously large bust-sized boulders and don't think of the tiny bubbles. But that's a great question. We know from the engineering literature that can be such an important process, and where we've got hydraulic jumps and a ton of turbulence, this it might very well be. And we don't know if the boulders that we're looking at were plucked from the bed, from fractured materials and blocks that were protruding and were able to be transported. We don't know if that was it or if they were knocked in off the hill slopes and then transported. But perhaps if you had a lot of cavitation, that could make fractures bigger and make it easier to pluck for all we know. So that's possible.
Okay, so we have a question from Audrey. I'm sorry, I can't pronounce your last name. Margarita. She says, do you have an idea of the respective contribution of big floods versus monsoon flood power on gorge erosion at a million-year timescale?
That is a question too. This is actually something that Susanna Mori has worked a lot on. And because originally we're thinking, okay, we've got this provenance signal that says that there may, hints at, we've only got 3 size events, but may hint at there being some threshold where the largest events are doing something different, where they're focusing erosion in the gorge. And so we thought, okay, well, let's compare flood power to stream power. And the idea, so we did those calculations, and actually flood power, we expected to see sort of that maybe if it were the case that maybe you see, okay, yeah, flood power is bigger everywhere, but we would expect to see it be like extra big in the gorge compared to the offset that you would see downstream. That's actually not what we found. And so we're like, okay, well, maybe flood power isn't the right thing. Maybe we need to talk about energy expenditure, because the floods last hours and days and the monsoon lasts months. And so we put the time scale in, and that lets us get an energy expenditure. And so then we expected, okay, well, maybe in the gorge, the offset will be bigger between flood energy and river energy and smaller downstream. That's also not what we found. We found that actually the differences are not as systematic. They get a little bit more systematic as you average those values over larger scales, like 50 kilometers, as opposed to like a kilometer or 10 kilometer windows, but still not a clear signal. And so we actually think that the key here is that just looking at the river channel and power or energy calculated at the channel is not, it's missing a huge impact of the megafloods on the hill slopes. So we really think that we're not able to capture this in sort of using these metrics that are made for rivers, because the action is happening on the hill slopes as well. We're inundating hundreds of meters with enormous shear stresses that can rip off anything that's at that surface. And so thinking about power or energy expenditure, I think is actually the inundation itself, and the fact that you're having such high shear stresses on the hill slopes just is fundamentally changing how you're able to erode. And then the river's really powerful, even in between events, and can flush sediment through. So I think that, whether a perturbation from a big flood, I don't know yet the timescales over which those effects of the hill slope are going to really swamp the river. But anyway, that's the evolution of our thinking. We went from power to energy to thinking, okay, we're missing things entirely. It's got to be the hill slopes.
Perfect. Okay, so we have more of a statement than a question from Shukla. Says, I think sedimentation is a bigger problem for Brahmaputra than flood.
Well, that's Yeah, sedimentation. Well, if you're a sedimentologist, maybe you love the sediment, but if this comment is about the impact on people, this is a huge issue for people today. The outburst floods are happening all the time. Landslide outburst floods are happening all the time, and as glaciers recede, we may be getting even more outburst floods from that process. But I think what's really interesting is thinking about these big events, yeah, down in the transfer zone, like Jen Pickering's work has shown, where we're thinking about how these floods actually change the course of the Brahmaputra and maybe even responsible for major avulsions. And because they can transport gravel and boulders, that can then set up interesting situations where you're armoring channels in that downstream region. And so, yeah, effect on the sediment, and not just the mass quantities of sand that are being deposited, but also the flows themselves and how they can move different grain sizes that then change the form of the channels, where the channels occur, and how they might be armored, so that changes the routing system for who knows how long afterwards.
Yeah, so we have another question by Shukla. So can the tributaries from Naga Hills also contribute to sediments?
That's a good question too. I mean, the tributaries, I guess it depends what the flow, how much material can be evacuated and what the rates are. I mean, the highest rates of rock uplift are certainly to the north of there, but this is an area, this is also a seismically active region, and so you could certainly have landslides and a lot of sediment delivery from the hill slopes that gets into the river and eventually contributes sediment as well. I don't know if that answered your question.
All right, so I see that we now have another question from Nadia Intel, which is, what is the cause for more rapid exhumation at 5 to 7 million years ago?
Yeah, so I guess I kind of like the Bendick and Ehlers model, which was a sort of a generic look at what syntaxes should do, and it just sort of predicts that eventually, due to the subduction geometry, you should have some mechanical effects that would cause exhumation to really spike. And so that's a sort of a hand-wavy hypothesis that inspires me at the moment. But that's certainly something that I think, as our ability to really understand the rheology improves, this is something that I hope the geodynamic modelers attack more.
Perfect. Okay, so we have another question from Ben Everett. He says, your cross sections and aerial photos suggest steeper valley slopes on the outside of bends. Do you have a feeling for the long-term meandering of the bedrock valley?
Yeah, so I don't know for sure. I don't know if I can speak to whether the steeper valley slopes are on the inside versus the outside of bends. And thinking about, let me just look at that question. Thinking for the long-term meandering of the bedrock valley. So I know that on the scale of tens of thousands of years over which we have these records, we are incising the valley in this rapid area, and lateral migration of the bedrock valley is something that we're really interested in studying. So I don't think we have any empirical constraints on it at this point, but this is a major focus of the work that Susanna Morey is just starting now, as of like last week. She downloaded the break model and started working on it with Charlie Shobe. And so one of the ideas is that we want to look at not just the effect of boulders on longitudinal profile development and potentially stepped profiles, but previous workers have shown that boulders are really important potentially for impacting how lateral erosion occurs, which would be key for this idea of meandering of the bedrock channel. And so Susanna is trying to implement a lateral erosion component into her modeling study, and then delivering blocks of the sizes that we observe in the field and the kinds of distributions we observe in the field, and then putting through flows of the kinds of discharges that we know happen with the monsoon and that she's modeled and simulated to try to get at this question of the lateral evolution of the valley and as well. And so then there's always the question, how much is the valley versus how much is the channel? So we're thinking about the channel and what that means for what annual flows can do. But during the megafloods, you know, during glacial times, the effective channel during a megaflood is up here. And so what does it matter for a megaflood? It might matter if you have a ridge that's 100 meters up, it is what might matter for flow conditions there. And so it's a tough question to think, what could that do to changing the meandering of the bedrock river when maybe the channel forming flows are these infrequent events that happen during the end of the glacial times.
Okay, so also we have, well, I suppose it's not a question, but an answer from Jen Pickering that replies, she says, in reply to how floods impact Brahmaputra, Ryan Sienkiewicz has a paper just ready to be submitted on some modeling work that suggests that the western Jamuna pathway of the Brahmaputra in Bangladesh has persisted throughout the Holocene, specifically because of megafloods scour 11,000 years ago. So the flood has influenced the topography in a way that the Jamuna is not able to move into and stay in the old Brahmaputra pathways on the Silet Basin side. I'm sorry for butchering all the names, which should be preferred based on slope. So that's a great answer for some questions that arose here.
Awesome. Yeah, that's the precise version of my saying that you know, Steve Goodred's group and all these people are making these awesome observations in the subsurface of this system, of these big cobbles and things that are really setting the channel form and then making it hard for the river to even follow its steepest descent path.
Yeah, if I may, I have a personal question. So for the simulations that you run, so did you have access to a DEM with the bathymetry of the river? And so you also make an assumption about the fact that the current topography can be used to simulate this past flood. So do you have some comments on that? And
Oh yeah, that's a great question. So the flood simulations we've shown here were on a 30-meter DEM that Mike Trusewski made. And that, you know, at the time it was like, okay, 30 meters, and we set our maximum resolution of our adaptive mesh in the modeling to match the resolution of our topography. And so for the megafloods, it is absolutely good enough. This doesn't have the bathymetry of the channel, and the megafloods don't care because they're 100 meters deep. But it does matter for the historical outburst flood. So that landslide dam outburst flood, Mike Trusewski did a lot of really careful work of basically matching the inundation paths where they're most sensitive, the inundation heights and the simulations where they're most sensitive to these effects in the lower part of the valley, where you've got this wider valley and you have significant bathymetry and topography there. And he found that basically you could, more important than the bathymetry probably is actually the addition of the monsoon flow as a base flow at that point in for that size flood event. And so by sort of adding on the amount of monsoon inundation, we could explain the discrepancy between our simulated values and the inundation that you see. So the bottom line is that no, we don't have bathymetry. The simulations, even for the smaller flood event that should be sensitive to those sorts of things, it looked like you could explain our any discrepancies between our simulation inundation and the observations of the trim line from the actual flood by just adding in monsoon flow, which we hadn't explicitly treated in the model. So that tells me that it's probably not a big deal to be missing the bathymetry for getting the inundation patterns and shear stresses. But that's different from, that's like saying, okay, we're using modern topography. And so in this sense, with modern topography, we're looking at, certainly it changed through time and during the floods, potentially, but we're looking at it, we're imagining it in terms of what is the most recent flood, what would it have felt, what are the deposits we see today? And so, and if the river subsequently wasn't able to modify the system as much as those largest flood events afterwards, then we're like, okay, well, this is giving us a sense for the kinds of scale features we would see. And so in a for building intuition in terms of what is a flood going to do through rugged topography, using the modern topography is great. And I think that the resolution of the techniques and the questions we're asking does not yet demand trying to figure out what paleotopography was like. And instead, we're approaching it from the perspective of process modeling to see okay, what kind of lateral erosion, what kind of incision, what kind of stream power or stream profile development should be happening during these floods, as a way to develop a sense for knowing how far off we might be by looking at the modern topography. So I don't know if that answers your question.
Perfect. Yeah. Thanks.
Okay, so we have another longer question. Due to global warming, as temperature rises, most of the Himalayan river faces abrupt flow due to seasonal fluctuation, as sometimes the Ganges River changes its daily discharge that is difficult to monitor the flood. As previously, we had some knowledge about the last 10 years flood season, but now it's not possible to monitor from previous records. So how could it be possible to monitor the flow, especially in floodplain areas in West Bengal, Ganges-Brahmaputra Delta, where previous flood records play an important role?
Oh, so I'm not, so just sort of what I'm taking from this question is a sense for how do you figure out what are even representative modern flows and their variability, to even get a sense for what that might be. And this is something that's difficult to measure. In the hinterland, at least you've got a confined channel and you can measure in the same place every day or every year, every week, whatever it is. But as you go out onto those broader areas, this is a place where, in the braided stream, the active channel, it changes absolutely seasonally and also during season. And so trying to come up with, I agree. I guess this is less of an answer than yeah, I think it is a really hard thing to measure. And more importantly than that, it's hard to measure, and then also hard to measure something that's representative and useful for figuring out what the discharge is if you've got these channels that themselves are really complicated and changing constantly. So thank you for that comment.
So we also have a question by Chanyan Wang, sorry for the pronunciation. So thanks for this nice presentation. So his question is, what is the first controlling factor, slope of the river or the high discharge from dam break? I guess what is the effect on erosion and transport?
Yeah, well, that's a good point. I mean, I guess I would like to know, who's going to win in the battle of what's more important, the slope or the discharge. The slope certainly is really important, but in these large discharge events, if we think about where the transition from primarily these extremely high shear stresses and extremely high flood power of those values that are sort of more than 10 kilowatts per square meter kind of thing, that are more indicative of erosion, they do coincide with the higher steep slope areas, as you might expect. And so clearly setting up that steep slope, which we're arguing is something that, you had an antecedent river that then the rock uplift oversteepened, I think that's got to be a major control, if not the major control. And then to watch what superimposed on that these enormous discharges do. Certainly you have the highest erosion potential in those steepest zones of the gorge, and then you get to the lower values of stream power. Still really freaking high, like you can move these big boulders, but because the stream power values are a little bit lower, based on studies from the Missoula floods, where Denlinger and O'Connell did similar modeling study to us on a very different kind of topography, and then compared it to erosional versus depositional features, those sorts of threshold. I'm getting this idea that deposition happens here, or erosion should be expected there based on flood power on the basis of their observations. From that, I really think that it's about, you know, I think the steepness of the river is telling you a lot about the power to erode and what and also the hill slopes to keep up. But ultimately, when you're putting big flows through, you got to also think about how that's going to interact with the steepness of the river. So that didn't answer your question. I didn't say I'm not willing to place bets on which is more than the other, but you know, the steep channel profile, I think, is got to be a major control. And maybe it's been argued that the impoundment of dams right there at Namche Barwa is something that has helped to maintain that nick point so that it hasn't, you know, chewed back into the Tibetan plateau as much as you might have expected to. So maybe they conspire, maybe the floods and the impoundments conspire to keep that that steep spot steep. Is sort of what we're arguing here.
Perfect. Okay, so we have no more questions. Anyone has a last question, you can throw it in now. There's lots of people in the chat saying excellent presentation, Kate, so well done. And I really enjoyed that, and it's super clear as well. Okay, so we have no more questions. So thank you very much, Kate.